Hi, I'm Matthew. Today we're going to be talking about benchmarking programs on the different types of data paths we talked about in lecture: single cycle, multi-cycle, and pipeline. Here you see we have the latencies for the different components of the data paths we talked about: reading and writing from memory, reading and writing from the register file, and doing an ALU operation. And then down at the bottom, we have the percentages of the different types of instructions that we have in a certain benchmarking program. And if we assume there are 1,000 instructions with those percentages operating on a single cycle or multi-cycle or pipeline data path with these latencies, we need to calculate the CPI, or cycles per instruction, and the execution time of that benchmarking program. So to start off with, we will start with the single cycle data path. And for the single cycle data path, finding the CPI is very easy because the CPI of a single cycle data path is always 1. And that's because it's cycles per instruction, and every instruction in a single cycle data path takes 1 cycle, as the name single cycle would imply. So we can write that to begin with: CPI equals 1. To figure out the execution time of a program in the single cycle data path, we need to figure out what the clock period of the single cycle data path is. The clock period in single cycle is dependent on the longest running instruction. That means that even if we have instructions such as no-op that don't use very many components and could execute in a very short amount of time, they'll still take the same amount of time to execute as the longest running instruction, because since we only have 1 cycle per instruction, we need to have the clock period fixed to a time that is large enough to accommodate the longest running instruction. So for a single cycle, the longest running instruction will always be either LW or SW. And in order to figure out which one it is, we just need to add up the latencies of the different components that each of those instructions uses. So we can start off with LW. When you execute an LW instruction, any instruction always starts out with reading from memory. So reading from memory for the LW instruction takes 30 nanoseconds. And then you need to read the values from the register file. Register reading takes 4 nanoseconds. Then you need to perform an ALU operation to add the offset field to the value in register A, and the ALU operation takes 12 nanoseconds. After that, you need to actually read from memory again to get the value from memory that you want to put into register B, so that takes another 30 nanoseconds. And finally, you want to put that value into a register, which is a register write, and in this case, it takes 7 nanoseconds. So the total time that it takes an LW instruction to execute is 30 plus 30 is 60, plus 11 is 71, 83 nanoseconds. Now we'll do the same thing for SW. The SW command also needs to read the instruction itself from memory first, then read the values from the register file, then perform an ALU operation between the value in register A and the value in register B. So these latencies are all the same because they use the same components. But then instead of reading from memory and then writing to a register, we do a memory write to that location in memory. So this latency is 42 instead. And when we add up these latencies, we get that the amount of time it takes for an SW instruction to execute is 88 nanoseconds. That means that in this specific case, the SW command or instruction takes longer to execute than the LW command, and so our clock period for the single cycle data path is fixed at 88 nanoseconds. And with that, it's now very easy to calculate the execution time of the entire benchmark. Because we know that we have 1,000 instructions, and we know that each instruction takes 1 cycle, and each cycle takes 88 nanoseconds, we can just multiply 88 times 1,000. To give us 88,000 nanoseconds for the execution time of the entire program. And now let's move on to the same program in the multi-cycle case. So now that we're talking about a multi-cycle data path, we're going to need to worry about the actual percentages of the different types of instructions, because unlike the single cycle case, each instruction doesn't necessarily take the same amount of cycles to execute on the multi-cycle data path. So to start off with, we want to calculate the CPI of the multi-cycle data path. And to do that, we're going to need to use the percentages of the different types of instructions to figure out how many cycles total the program takes to execute, and then we can divide that by the number of instructions to get the CPI. Remember that in a multi-cycle data path, this is the number of cycles each of these instructions takes to execute. Add and NOR both take 4 cycles to execute. LW is special, it takes 5 cycles to execute. SW and BEQ also take 4 cycles to execute. And then NOOP takes only 2 cycles to execute, because it just needs to read the instruction and decode it, and then figure out that it's NOOP and move on to the next instruction. In general, LW is the only instruction that takes 5 cycles to execute. All of the others, except for NOOP and HALT, take 4 cycles to execute, and then NOOP and HALT both take 2. So knowing that each of those instructions takes that many cycles to execute, we can figure out how many cycles total the program takes to execute. So we have 1,000 instructions, and that means that if we have 25% of them as LW, that means we have 250 LW instructions. So we can do 250, and each of those 250 LW instructions takes 5 cycles to execute. So this is LW. And then all of the ones that take 4 cycles to execute, we can add up their percentages, and that's 30 plus 30 is 60. So there are 600 of these types of instructions that take 4 cycles to execute. And that's for add, NOR, SW, and BEQ. And then lastly, we know that there are 150 instructions, the NOOPs, that only take 2 cycles to execute. So we can do 150 instructions. So 150 instructions contribute just 2 cycles to our total. And if we calculate all this together, we will get the total number of cycles that the program takes to execute on the multi-cycle data path. And that is 1250 plus 2400 plus 300 is 3,950 cycles to execute this program on the multi-cycle data path. So now that we know the number of cycles, we can very easily calculate the CPI, cycles per instruction, by dividing by the number of instructions. And that gives us 3.95 CPI. And now if we want to calculate the execution time, we need to do something very similar to what we did in the single cycle case, where we take the number of cycles and multiply it by the clock period. But this time, unlike the single cycle, the clock period isn't defined by how long it takes the longest instruction to execute. It's defined by how long the longest component takes to execute in each of these 5 components. Because the idea of multi-cycle is that you're only having one of these components executing at a time. So you know that each clock period can execute just one of them, and so the clock can run, in this case, every 42 nanoseconds, because that's the time that it takes for the longest component to run. So if we assume that our clock period is 42 nanoseconds, we can figure out how long it takes the entire program to execute by taking the number of cycles and multiplying by the clock period. So that means 3,950 times 42 should be the execution time of the entire program in nanoseconds, and that comes out to 165,900. As the execution time for this program in the multi-cycle case. In this case, it does take a lot longer to run than the single cycle case, which does show that in some cases, the multi-cycle processor is actually worse in execution time than the single cycle processor. And now that we've done that, we can move on to the pipeline, the best, in my opinion, the best data path, and see how we calculate the CPI and execution time there. So when we're calculating the CPI and execution time in the pipeline, we're going to assume that there are no hazards, no data or control hazards. And we're going to be talking about those in the coming videos, but for here, we're just not going to worry about them. So when you're working with the pipeline and there are no hazards, and you want to calculate the CPI, you need again to find this number of cycles that it takes the pipeline to execute. Now the idea of the pipeline is that because it executes instructions in stages, it should take about one cycle to execute each instruction. Because every instruction moves down the pipeline, one step every single cycle, and instructions are inserted into the pipeline at a rate of 1 every cycle. So the number of cycles that it takes to execute is just the number of instructions plus a few extra cycles to give us time to fill the pipeline at the beginning before instructions start completing at the end. So the total CPI is the number of cycles divided by the number of instructions. The number of cycles is just the number of instructions plus 4, because we have 5 stages in our pipeline. So we'll be inserting 4 instructions into the pipeline before they start completing. And after that, they'll start completing at a rate of 1 instruction every cycle. So it takes 1,004 cycles to get all of our instructions through the pipeline. And then we just divide that by the number of instructions to give us a CPI of 1.004. And in general, the CPI of the pipeline should be very, very close to 1 because we're putting through about 1 instruction every cycle. So now when we want to worry about execution time, we again need to take the number of cycles and multiply by the clock period. And just like in the multi-cycle case, the clock period of the pipeline data path is dependent on the longest running component of the data path. In this case, that's writing to memory, which takes 42 nanoseconds. And so we can say our clock period is 42 nanoseconds. To find the execution time, we just take our number of cycles, 1,004, times our clock period of 42, and we get that the total execution time is 42,168 nanoseconds for the pipeline data path, again, assuming there are no hazards. And that's a lot faster than both the multi-cycle and the single-cycle CPU, which is why pipeline CPUs are how actual CPUs are implemented in the real world. And so this gives an overview of how you would tackle these problems in both the single-cycle, multi-cycle, and pipeline CPU cases.